in honor of our incredible guest and of a fantastic host, because we've been taking everything for granted, but Bob Walters has produced an incredible meeting today for all of us. I was noticing while Bill was talking that at a certain point he mentioned the possibility of connecting large chunks of things which have no connections whatsoever. I'm quite convinced that there are people in the audience that do not know who I am, and I don't know who they are. But we all know Bill and Bob, and I want to thank both of them for having done this incredible. And now after that, I don't know for how long I've known Bill. No, very quick, but it's, I've known his work before I met him. I studied some of his papers when I was a student, and I remember very well I didn't understand them. And certainly I don't understand them now yet, I'm sorry for that. But I have tried very strongly to apply what he has been saying about the usefulness of category theory and topos theory in teaching parts of mathematics. And so I have a direct question immediately. Since I am a logician, basically, and I have to teach logic, I teach logic to students, especially in the first year undergraduate, using the slogan of the quantifiers and the connectives as adjoints. It works because it is a simple rule, it's always the same. I don't have to tell them what an adjoint is, of course, I don't tell them what factor is either. But the rules are all the same and in front of them, and they understand essentially that logical consequence, or call it whatever you like, inductive relation, is the crucial concept about logic. Have I done it wrong?
Sounds like a great start. What do you mean wrong? What do you have
okay, for instance, then I do have to teach them another course in logic, and of course there are some of my colleagues who want to be sure that they know about Hilbert systems, about Gensen sequence calculus, and so on. And so I start, and I found it easy to produce translations in the strict sense of the word, logical translations, from one deductive system to the other, starting from the calculus of adjoints and the consequence. And is it wrong to move away from one deductive system and talk about others, or should one, or could one do that anyway?
Well, several deductive systems.
Yes, exactly.
I don't know if it's directly connected to what you're saying, but I think a crucial thing to emphasize is the word presentation. And the fact that most of what's called logic is really presentations of something. So the distinction between the intrinsic thing, where the adjoints are literally functors, and presentation, which they're just symbols, but symbols treated in a certain way so as to affect that presentation. And the fact that this is something totally analogous to presenting a community ring, say, for certain variables and certain equations and so forth. In other words, I've said it in a very extreme way somewhere. I've said that most of us topos theorists, speaking for everybody, we think of logic as a sort of special branch of algebraic geometry. Right? Although however deeply we want to go into that, it's another question. But the idea that there are these three things, that there are the abstract generals and the concrete generals and the presentations of each. I think it's quite a... because, you see, the treatments of logic in the 20th century have always presented the syntax first, so as to say that the only possible meaning to the abstract general is you take equivalence classes of strings of symbols. But I think this is wrong, even according to historical conceptions. I don't think one would have thought of the predicate calculus. Let's say even the proposition of calculus as such, unless one had, again, what I was saying about Hegel, an idea that there is something like a system of conjunction and disjunction, which is an algebra. Maybe not consciously so, but somehow this, you must have this idea before you start presenting it. You have some vague idea of what it's supposed to do as an algebra before you start presenting it. And you also realize that you could have several presentations because, et cetera, et cetera. So somehow, I mean, if I were teaching logic, I would be sure I would want to bring in that distinction as well.
So I'm doing it right, because at the beginning when I teach connected as adjoints, I don't teach about presentations. I don't talk about presentation. I do have to talk about presentations when I then start presenting the other systems, because I have to make sure what the formula is.
Yes. But you can have some kind of conceptual clarity before you have a presentation. Having presentations always leads to more conceptual clarity.
Yeah.
But the thing you want to have clarity about is primarily the concepts. Of course, unless you want to program things, then you'd have to have the syntax straight as well.
Can I waste 10 more seconds?
Does this answer your question?
Yes, it does. Yes. I mean, it makes sure that at least I'm just about to pass the exam, maybe. But you should know that there is a computer program supporting the students to learn this approach to logic. And in one of the manuals, you should know, there are all the rules of the adjoints for connectives, and the manual has a nickname at the top, which is Lovia. You can continue to use it.
I have to ask my lawyer. She'll say yes. Well, it's again my own interpretation of things that Lenin said and Hegel said, and so we're always trying to actual mathematics as the primary model. So you see that this is a method. Mathematics is the almost sufficient content taken in its broad form, sort of philosophical. No, it's the idea that a concept consists really of two aspects: the theory and the category of models. For example, in my language about algebra, algebraic theories, categories of models. The notion of group, for example. Slavishly following Frege's mistaken instructions, you would think, well, group could only be the class of all groups. Well, that's what it be, right? But in fact, it's determined by the theory of groups. And you could even say that the concept of group is the theory of groups. So really you can't do without the two. But then, I suppose, put it maybe in the most general terms, too general, it's like a fibered category. Right? Because you have the base, which consists of the abstract generals, and the fibers, which are the corresponding concrete. This is a doctrine of these things. Some way, the fiber category is a way of systematizing a certain kind of abstract concrete duality of concepts.
But those are not the only two which you use some of that.
Again?
You talk about abstract general, concrete general, but also concept terms or something.
Well, there's the. I think the concept of structure, as I was saying, is very big. A lot of confusion because of this Frege and then the extreme superficial philosophers who try to deduce from Bourbaki that everything is structure. Just maybe not quite as bad as Frege's claim that everything is. See, I'm talking about concepts. Frege actually says we might as well, without any justification, as I read it, we might as well identify concept with property. So then, of course, you can only have property if you have a single universe, and everything is like a subset of that universe. Anyway, so both of these are deficient. So I think that I was speaking with Christian Bruxelles or Paris a month ago. And he remarked on his own, he said, there is this thing, see, if you have a construction, as a result of the construction, the things that you produce have structure. So in other words, more specifically, if you have a functor, you might have thought that the codomain was groups, or you might have thought it was sets, but actually it's always more than that in principle. Just because you've constructed it in a certain way, starting from a certain domain category. So now there are the ordinary natural transformations on that functor to itself and from its powers to itself. So those natural transformations constitute now an abstract general. You take them, of which a concrete general is a richer category that sits over the original codomain, and the original functor automatically by definition lifts to that. So it's in that context that the notion of descent comes up. There's sort of a philosophical notion of descent. Every interesting mathematical problem is of the sort. There's this process that's pretty obvious to me, but I'd like to invert it. I would like to invert it, and that's arbitrarily hard, even in the technical sense of hardness. But the inverting it, you see, so in some sense the first step toward inverting it is this lifting to the higher structure. And then you could hope that the lifted functor has an inverse. Typically, it at least has an adjoint, you see. So again, the second step is the idea that an adjoint is an approximate inverse. If you have these two adjoints, and before you try to do it, you have to find a new domain, which is things that have all the structure. Okay, well, in my thesis, I had, finite product doctrine, and so you had what I call algebraic structure, and you had semantics of the structure. So this is really the semantics of the structure that you get here, of this given thing. So a given, you might, the category you start with might or might not have been the one that was structured according to the doctrine, but in any case, if it were, you'd be getting a map, the usual map, double dual map to the composite ideal structure, and semantics are completely different. So Husserl said this to me, that this must be a basic philosophical concept. Great, I said, I agree with you completely. But 40 years ago in Zurich, I told this to John Beck, and he said, of course, he was also working very closely with this related doctrine about the theories of the monad. He said, this actually sounds like what's called descent as well. See that in geometry, algebra, for example, there's the problem of descent. And what's not there is instead of looking at these natural transformations, you say, well, if the thing really arose that way, and if I pull it back in two ways, there must be an isomorphism between two pullbacks that arose from the fact that it came that way. If I just had a plain object, there would be no such structure, but if the object was the value of the original functor, yes, it will be, and it will satisfy some so-called cocycle condition when I pull back in time. This is in the context of the whole. That was called descent data. And the problem was that the category of all objects equipped to descent data might be equivalent to the category. So in which case, it said that the descent is successful. So the idea is that this extra structure